go. All right, yay. Here, what is asynchronous programming? We're going to talk about sequencing and forking and testing synchronously, okay? So there's 2 points of this talk. One is general patterns around how to use Scala features and what those patterns are named in functional programming. Those patterns actually have far greater impact than we're going to talk about today. We're going to just talk about them in context of features. The testing synchronously bit we might not get to. So who am I? Already said that, yay. Okay, this is in a series of talks I like to call the new web. These are like the buzzwords you're going to hear, okay? Today's talk talks about doing event-driven asynchronous composition of services. All right, the basic gist of this talk is we have a big stack trace, never mind. Okay. That's because of my network, I think. The source code is under Suereth/intro to FP, if you want to take a look. The source code is an application that goes and grabs a bunch of data from GitHub. We're aggregating a bunch of different calls. Okay, we have an asynchronous, we're using dispatch, data binder dispatch by Nathan, one of the organizers of the conference, to asynchronously grab data out of GitHub, and we make several calls, and we want to make a aggregate service that is still asynchronous, that is still deferred in the future. And that's essentially what the source code is doing. We're going to go through the patterns of how you aggregate other asynchronous services to create a new asynchronous flow. All right, what is asynchronicity? It's not as crazy as it seems. It's just an operation happens upon receipt of an indication. All right? There's nothing magic about asynchronous code. Asynchronous, you can have something that's asynchronous and is terribly unperformant. Asynchronous is not special scaling sauce. It's just after something happens, I do something else, okay? So for example, this is asynchronous. I want the datas. I have my servlet thread that then the user tells me he wants the datas. I go and make a JDBC call. He hits the database. That comes back to the JDBC connection thread, and that comes back to my servlet thread, and I tell the user. I block 2 threads for a pretty long time during this process, but it's asynchronous, right? The code runs on receipt of some signal. The database was ready. But I'm still blocking the thread, so that's bad. What we want to do in Scala is called asynchronous and non-blocking. Okay, that's the key, is both of them. The assumption is, if I give up the thread and let somebody else use it, they're going to make better use than me just holding on to it. Because this query will take a while, okay? It's somewhere else. That's the general assumption in terms of when this practice is good, okay? All right. Those are the points in time where somebody else can use my thread. So, in Scala's future, we can define a future. It's a lot simpler than in Java. We just say future and then a block of code, and that block of code will execute sometime later. And we'll get basically notifications when it's done. We can chain new operations asynchronously on it. So I can say map, I can take the previous value, and I can get a new value after that. I can put a computation to run after the first value is done computing somewhere else. The asynchronous piece is this chaining, this take the previous value and do something else with it. The non-blocking piece is that futures go off and do something somewhere else and my current thread can do something, okay? All right, so why not use Java's futures instead of Scala's? Java has a future, right? Here's a really good example, just creating a future. The difference between Scala and Java is kind of intense. But more importantly, it's about chaining, okay? It's about asynchronously chaining behavior and ending up with a future at the end, okay? It's the ability to define a flow of computation in your program and have that be asynchronous. And really, the goal is never having to block, never having to get the value out of the future if you can help it. That's what you want. So, we're going to talk about sequencing, which is map and FlatMap from functional programming. We're going to talk about joining, which is zip and traverse, okay? So, let's talk a little bit about sequencing. Let's say I'm developing, say, a web framework, okay? And I have an asynchronous API to my data store. So I'm using Mongo's async driver, or I'm using the Postgres async driver. I'm not using JDBC, okay? That's key. JDBC is not asynchronous. I execute my query and I get back a future database result. And then I want to take that result and I want to do something else with it. So I map it. I map the data that I get back from the query and I generate some HTML. Now I have future HTML That future HTML is done after the query is done and after the HTML has been rendered. And it happens on some other thread, I don't care. When that's done, I need to write it out to the socket, so again, I map it. When this is done, go run this code, okay? Write it out to the socket. And the socket I get essentially in the handle request method, we'll assume that. So if you look here, I have a flow of futures. I never actually get the result out of the future, but I still accomplish an end-to-end goal of computation, okay? Futures are a way of flowing together computation. It's basically a runtime. All right, let's say I refactor my method now. That's what map is essentially. After one future is done, I have a computation I run with its result and do some more stuff. Let's say I refactor though, and I make my render method, and my render method has to go off and do some other complicated things that it needs to do using futures because it's going to defer some calculations until something's done. So my render method now returns a future of HTML. All right. So after I get my database query here, I'm going to call map on the result and render it. But what do I get back from map? I get back a future of future HTML. It's nested. If I want to, I can't, I have to defer into the future, then defer into the future. So these nested maps and everything gets really, really ugly. We have a solution for that. It's called FlatMap. Okay, for those who are unfamiliar with Scala's collections, FlatMap is used in there. If you're unfamiliar with this concept, essentially what you're doing is you are flattening and mapping at the same time. Where flattening is, if I have a future of A, I get back a future of A. If I have, say, a list of A, flattening gives me back just a single list with all of those lists aggregated together. With futures, it's a little bit different. It's just a way of saying when the inner one is done, I want that guy, not the outer one. Okay? Does that... I know I'm talking fast, but we're like 5 minutes behind. Sorry, guys. Okay, so FlatMap fixes the type signature, so now I can delegate to another asynchronous method. So if I'm chaining a set of asynchronous methods where I take in some input, get a future of something, I'm using map and FlatMap, okay, to chain these things. In Scala, we have syntactic sugar for that. It's called a for expression. So just like a collection, I can use a for expression and say, for the data I get from the asynchronous query, call render with that data, and then give me the HTML back, and then yield, finally go write out the HTML. All right? Using for expressions. It's akin to what you do with collections. You can think of futures as a collection of just one element, and if I iterate over it, I'm essentially waiting until that future is done to execute code. Okay? But this is essentially how we do future flow in terms of sequencing. The query has to return first before I can call render. That's key here. Render does not get called until the query is finished. I'm not doing two things at the same time. I'm doing this, and then this, and then this. Okay? Monadic flow is kind of what I'm calling this. The fact that we can do this is because we have a monad against futures. For those of you who aren't familiar with monad, it's a really funny term. Comes from category theory. We'll talk about that specifically, but there's essentially an interface on future that allows us to use for expressions in this style. Okay, and this is a flow, a sequence of operations. Monads are actually more powerful than just defining flows, but that's what this pattern is. Okay. So what is it? I have a series of operations I need to run. Okay, I can run them inside of a future monad. I can run inside a synchronous. I can run them inside of a collection. So that is where I have a collection of things and another collection of things, and I'm digging into collections like a tree. All right. Have you used it before? Anytime you use for expressions, you're using this concept. What I'm trying to show you is that it's not, for expressions are not just about collections, it's about computations, okay? All right, so if you have map and FlatMap and some sort of factory method, that's all you need to use this pattern. That's the basic of it. It's really, really low level and abstract. All right, now let's talk about joining, because this is more exciting. This is when we actually can compose services, all right? If I have a query to go get the users and a query to go get projects, because say I'm GitHub or something, and I want to join these two things together, I use what's called zip. All right. So let's take a look at what zip is. If I take users and projects, I have a future result for both, and I zip them together, I get back a tuple, where the left-hand side is the one query result, and the right-hand side is the other query result, okay? Looks like that. Joins them together into a single future. So they both execute concurrently at the same time, possibly, depending on how many cores I have and how many are available, but they could potentially run at the same time, and then when they're both done, this new future is complete. So it's how I take two different flows, join them together, okay? So that's zip. In the actual, the pattern we're going to call, it has a completely different method signature, but for now, zip is efficient enough for us, okay? What about collections? Let's say I have a list of things that I'm doing sometime in the future, and I want to get back HTML. So I have a list of database results I have to execute, and I want to join all of those together and get back a single HTML in the future sometime, okay? Well, this is what's known as a fork join, okay? I have a set of collections, I have a set of asynchronous operations that are running on each of those items, and when it's all done, I join back together. So the components I have is I have a list of things, an async operation that takes one of those items and returns a future thing, and I want to get a featured list, okay? If I'm using map and FlatMap, it looks kind of weird. But there's this handy thing in ACA called, or in the Future API, sorry, called traverse. All right, traverse iterates over the queries, takes an asynchronous, it takes the queries, which is your list, an asynchronous operation, which is for every query I go run it, and I get back a future query result, and it's going to give me back a future list of all the results, okay? That's what traverse does. The method signature for that sucker looks really, really painful when you first hit it, but that's essentially all it is. I have a list, I have an asynchronous operation, or an operation within a context, and I want to get back a list of things inside of my context, okay? So a zip is essentially an applicative functor. If you have an applicative functor, you have a zip operation. Not necessarily vice versa, but anyway. So this pattern that we're using here is I have a set of operations that I need to run. And then when all of them are complete, I have a joining operation to combine the values from those initial operations, okay? So I essentially have an acyclic graph of things to do. How many of you guys are familiar with require.js? Anyone? Okay. For those of you familiar, require.js is the simplest example of applicative functors. I have a set of dependencies of JavaScript modules that I depend on when I define a new one. And once those are all initialized, it calls the function that initializes me, and I get each of those modules in as an argument. That's what require.js does. That's what applicative functors are, okay? And that's just a way of defining load order. Well, what else looks kind of like require.js? Spring's bean container crap is kind of like require.js, if you will. It handles initialization order. That's this pattern of joining computations. The pattern is so fundamentally simple that in Scala we normally look at Spring as being bloated because we see the fundamental pattern of just, if I have an applicative functor on some sort of context, I can join these computations together and make sure that the initialization order is correct. I'm defining my dependencies. That's what this pattern is all about. That's what we're doing with futures. Okay, it's just, we need that zip operation. What about traverse? Traverse looks a little bit different. What does this pattern look like? I have a collection-like entity. I have an operation to run against each element of that collection-like entity. And the operation returns values inside of the context that I want it to return values in. So when have you used this before? Well, traverse is the lowest level pattern for iteration over collections. If you look at Scala's collections hierarchy, what's the lowest level? Anyone know? Traversable. Yeah, traversable just defines what we call an internal iterator. All right, the collection, when I make use of traversable, the only thing the collection has to do is define how to traverse over each element and run a function against them. It doesn't actually give you an iterator that you can use. It says, I know how to iterate better. Okay, it's an internal iterator. It controls the iteration. That is what the traversal method here is doing, essentially. If you have one of these things, which is the simplest possible iterator to implement for any collection, you can make use of this pattern, okay? But it's essentially just iteration. And now we're going to go a little crazy, okay? So I was showing how to compose together this flow. If we take a look at code, is that readable? That's probably not, is it? Okay. So here's our GitHub service, okay? Our GitHub service is, I have a set of project statistics I want to run on a given GitHub project. What I need to do is I need to pull out the pull request from the API. This pull request, if you see, can you guys see the highlight? Oh crap, this is Eclipse, man. Yeah, hold on, let's just use VI. It'll be way easier. Source main Scala. Let's look at the futures one. All right, so we'll fix it in a sec. Okay. All right, is that readable? Bigger? Smaller? Okay. All right. So we want project statistics. We want to get them back in the future. But the project statistics we're looking at in GitHub, we're going to call it the Fort Knox statistic. So this is how hard is it for an external contributor to get their pull request in. And we're going to assume that over the last 100 pull requests, the percent that are accepted from outside contributors is going to be indicative of how hard it is to get a pull request in. That's actually a complete lie, but that's what we're going to calculate for fun, okay? So we grab all our pull requests, and pull request returns a future of a sequence of pull requests. We grab all our collaborators. The collaborators are people who have commit rights on the project. We have to grab it in a separate API call. It's a completely different API call on GitHub. That returns a future sequence of collaborators. Then we zip the two things together, okay? So we get a tuple that has our sequence of collaborators, a sequence of pull requests, and then we join them together in a map function. So we map that and generate our project statistics. Project statistics is a class that calculates all the statistics in its constructor because I was lazy. It's not actually a method, but anyway. So that's what it does. And now we want, for a GitHub user, we want to take a look at all those projects and see how their Fort Knox levels compare. So given a user, we get back, sorry, just checking time. We get back future statistics, and for each project of that user, we have to make an API call, okay? And we get back a future sequence of projects. So this project here is a sequence of GitHub projects. And then we traverse over each of them, right? Traversal. For every project, we make an asynchronous call, and we get back a future sequence of statistics for every project of the user, and we return back the statistics for that user and his set of projects. And then we print them out. And I'm going to run it, but it might, since the internet's been awesome here, it might blow up and do something weird. It's accessing GitHub as my user. We're going to compare Scala and Akka, which is a fun one. Yeah, those Akka guys, they're actually Fort Knox. Okay, so what would be ideal? I have this thing running in futures, but what if I don't want to run it asynchronously? What if I'm debugging and I want to run it synchronously? How do I do that? Well, actually, the way you do that is you pull out the abstractions for map, for FlatMap, for zip, and for traversal external to the context you're running in. So I'm going to fly through these. It's not important. You can look them up on your own. They have names. External map is what we call a functor in functional programming. Okay? I define a context type where it's a context that contains something, in this case a future, and I define a map method that, given a value in the context and an operation that takes the item in it and maps it to something else, I can get back a new context with that, adapted element. This functor exists for option, it exists for collections, it exists for futures, and it exists for something I'm calling synchronous, okay, which is identity. For FlatMap, it's called a monad. Yeah, it's a weird name, same as functor. But this is essentially the interface that I can extract, and then I can make use of these patterns. For zip, I can do the same thing with applicative functors. I can have an external zip. I take the two contexts and return the context. And for traverse, it looks different. Traverse, I need a collection. And the traverse method needs to know the context of the operations that you're traversing over. Okay? That's where I need an applicative functor for that context. Traversal can use any applicative functor, meaning it can traverse over a whole bunch of different contexts. I can go over, go read a paper called The Essence of the Iterator Pattern, and you will see all sorts of neat things you can do with traversal. One of my favorite examples is I can take a collection, and using a context of a half-filled out graph, I can go traverse and fill out the graph with the values from the collection, which is kind of cool. All sorts of neat, different, weird patterns. I'm just showing you the basics of the most common one that you will probably hit now. Okay. Then if I want to do synchronous or asynchronous, I take my statistics service, that user statistics service code you just saw, and I throw a type parameter for the context I want it to run in. Okay? Now, the implementation that I'm going to use is running it in the future, okay, with the futures. But that context, the only thing I need is a monad instance. That's what the monad is. It says that I need a value of the monad instance for this type. And if I have that, the entire service runs. Well, I can implement that for synchronous behavior, and then I can run my tests synchronously without having to defer and wait. Okay? Yeah. Not questions because we have to show you. I'll just show you. Oh, great. Yeah, internet. I'm sorry, guys. I should have printed out what it looks like. Yeah. Okay, so if you look at our testing here, when we do our test of the generic service, what we do is we define a new API, which is in the single-threaded context. Single-threaded is a type. I'll let you guys guess what the type is. Anyone know? Yeah, okay, few. We'll guess later. But essentially, when I define the project's method, I'm stubbing it out, and I'm stubbing out just returning directly some data, as if it's the GitHub API. And I do the same thing for all of the GitHub API, that abstraction I have, for single-threaded instead of future. And then I can just instantiate the generic statistics service with my single-threaded API that's stubbed out, and all my calls happen on the local thread. I'm not deferring things for futures, and I don't have to deal with the overhead and the complexity of threads and trying to wait for things to happen and figuring out, what's an appropriate timeout for this test. Like I have to wait for a certain amount of time for it to be done. Did it deadlock? No, it's all synchronous. If I get any sort of exceptions or anything, it happens directly. Okay, so what I've done by extracting out those patterns is now I can change the behavior of that flow of code. When we talk about functional programming, I mean that's a big thing in functional programming, is for the same code that I have, I can change the actual execution model. That's what things like monads help you do. Okay? So if that goal is worth it, and that's what you want to do, you go with the complexity of abstracting these things out, having the context, having the crazy type parameters and that kind of thing. If you're just doing stuff asynchronously and it's always going to be asynchronous and you don't care, maybe the overhead's not worth it for you, right? It's up to you to make that decision. I'm just trying to show you the power you can get by going that next level. So, I know we kind of flew through that because I had technical issues as always. I apologize. Any questions? We have 1 minute. Yeah. Why not use a for comprehension? Oh, okay. So one of the common mistakes that people make is when you do a for expression. Okay. Yeah. Come on. Import. Concurrent underscore import executor. No. Execution context. What is it? Implicit dot global. Yay. Okay. So one mistake people make is I want to do something in the future. So I'm going to println 1, and then I'm going to return 1 in the future. Okay. Then I'm going to do this thing here and println 2. All right? what's the problem here if I do, or sorry, not what's the problem, but do you expect these two things to run in parallel? A lot of people mistakenly assume that they're going to run in parallel, but they don't. The second future doesn't get spawned off until the first future is done. So no matter what, I always get x plus y. Wow. I did something bad to my SPT. Sorry, guys. Holy crap. Yeah. Let's. You didn't see that. Yeah, most people expect these things to run in tandem. You know, both futures run at the same time, but the first one will always run before the second one. Applicative functors is the only way that you can not care about execution order when you join two things together. Okay, and the other reason is that there are more things that are applicative functors than can be in for expressions, mathematically. So it's a looser restriction. It's easier to find things that fit that. It's easier to implement too. Yeah, yes? Yield really should be there. It doesn't need to be there if it's a future. Yeah, so with futures we have, the difference between having a yield and not having a yield is whether or not you have a for each method. If you have a for each method, you can use yield and get rid of all that complexity. But there's no harm in having yield, and there is harm if you don't have a for each method and not having yield. So that's why I have yield always. But that's the specific reason. Again, a future of unit I can just as easily ignore as something that returns unit. So, well, yeah, I mean, you can call get, right? But you need to figure out the right timeout for that operation when you call get. So in this case, it's a little trivial. It's going to return immediately. I stub things out. But when you're dealing with asynchronous code in general, there's always a question of how long do I wait for all the threading and locking and crap to end. That's the right value. You could use inf, but if you happen to have some sort of exception thrown and maybe things don't propagate correctly, your code gets really, really hard to debug. So the idea here is I want that synchronous flow, so when I step through a debugger, I see this happened, then this happened, then this happened, versus with futures, I have to start tracking things across threads. So it helps me write my tests, essentially. And again, if you don't need that abstraction for your particular code base, it might not be worthwhile to pull things out. If you do pull things out, you do have a lot more context in which stuff can run. Anyway, it's a trade-off. Yeah. Cool. Well, thanks, guys. Sorry I talked really fast. 30 minutes is awesome. And thanks for having me.